Hello everyone, welcome back to our AI engineering crash course. Today we'll implement retrieval augmented generation using different libraries that we saw so far in our course, which are LangChain, LLamaIndex, and Haystack. But before that, we had 2 modules about AI and AI engineering, 3 modules about AI engineering, the second about prompting, and the third about APIs. And this fourth module is about retrieval augmented generation and vector database. And today we'll just do the library part, LangChain, LlamaIndex, and Haystack. Concerning the project, we will be building the complete project on the channel, but not after this series here, because the project will take much more time and I want to split it in a different playlist. So if you would like to build alongside me the RAG project, the full project, and almost all the project of this crash course, don't forget to subscribe and yeah, get started. So this is the process we'll be implementing today. I actually explained that in the last video about retrieval augmented generation. We'll be loading a PDF, splitting the PDF and embedding it, creating embedding based on this PDF and storing it. For the moment, in all of the implementation we are storing this in memory. So we don't have a normal vector store, but you can replace it with any vector store by just replacing the instance and it will totally work. And in the second step, we'll just get a question, retrieve the related document, feed it to the prompt and feed it to the LLM, and then get an answer out of the LLM. You will see how different frameworks like LangChain, Haystack, and LlamaIndex solve this RAG retrieval augmented generation problem. As you can see here, we still have our LangChain memory. We stopped with semantic search here, where we just did some embeddings and similarity search from the embedding that we had, the in-memory embeddings. So let's just come here, let's put this in this global framework, and we'll create a new file here in the RAG called LangChain. Okay, so in this file, we'll be implementing the LangChain retrieval augmented generation. The first thing we need to do, we already have all the packages that we need. And if we need more, we'll just install them. But the first thing that we need to do is to actually import the necessary packages. And the necessary packages are actually just here. Let me just put it here and I will explain it to you. We have them here, okay? So we have the document just to represent a normal document. We have the PDF loader. We already used it. We have the in-memory vector store, which is the vector store of our whole RAG process, but just in memory. We have the OpenAI embeddings to compute the embeddings. We have the chat to just send the request to the LLM. We have the retrieval Q&A, which is actually the LangChain module to easily do retrieval augmented generation. We have the splitter here to split text, and then we have the env to load the keys. So the first thing, of course, is to load the env variables here. So we have OpenAI in the OpenAI API key in the env variable, and our LangChain module can use it. And the second thing is to create our vector store. Our vector store actually needs an embedding algorithm. We can pass many different embedding algorithms. Okay, as I explained it before, the data that we get is computed, an embedding is computed on that data and saved in the data store. So that's the reason why when you have a data store here, you need to pass a specific embedding instance. And this embedding instance in our case is OpenAI. It can be a specific package from Hugging Face or a specific provider like Anthropic or Google. You are free to choose here. We just choose OpenAI embedding here. Now we need to work on our document. Working on our document means loading it and splitting it. We already saw how to load a document. We use our module PDF loader. We pass the name of the file and we just call the load method. As you can see here, we have the loader. We call our instance of of loader and we pass the startup file and then we load. Here we have a list of documents. Now we need to split this document in chunks and we decide how large that chunk will be. We can use the recursive character text splitter from LangChain to do that. So what we do is we create a new instance of our splitter that will go through a given document and split it by chunk of 1,000. Why do we need an overlap? So if you get a text, maybe let me write some random. Let me look for some random text here. Okay, let me explain this to you. Let's create a new file. Let's say we have a text like this, okay? This is actually quite long. Let's say we have this text, for example, okay? Let's just go here so we can have the paragraphs. Just some lorem ipsum. Let's say we want to split it by, I don't know, 100 characters. Let's say the splitter cut this part of the text like this. We are just counting 1,000 characters and cutting it, okay? If we cut it like this, we will have a lot context, which means this part here before the dot will be lost. What we need to do is to keep one part of this and one part of this in each of our embedding, which means this is the overlap, to make sure that if you cut it at the wrong place like this, you still have enough information to augment and have the full picture of the complete text. So if you retrieve two different documents that overlap, will make sure that this kind of chunking here is prevented. Losing information in between chunking is prevented. So that's the reason why we have a chunk overlap here. So it will be splitting 1,000 and having an overlap and just keeping an extra just in case you cut it at the wrong place. Okay, and now we call the text splitter. Our text splitter will just split our documents, the documents that we get from this. Okay, pretty simple, pretty basic. As I mentioned, you don't have to do this yourself. The framework is doing everything for you. Now, what we need is just to save our chunks as on the image, okay? So this first part, it's quite simple, okay? I will show it to you on the text again. It's the first. So if you look at this again, we load the document, we split it, already done, we embed it, and we save it. So we did these 4 steps with these single lines of code. Okay. So now we need to create the second part, which is creating a model and querying this model. Okay. So now we need a new instance of our LLMs because we need LLM to do that. And for LangChain, it's pretty simple. We just create a new instance of our Q&A chain here with the retriever Q&A, and we pass the LLM. We pass the retriever that we have already. Let me check. Oh, sorry, I forgot to create the retriever. So the retriever is just here. It's just a module that will get the vector store and use it as a retriever, which means now we can send a sentence and retrieve the closest top K element that are that match that sentence. So now we pass it here, and we have this chain type to be stuff. So now next we have a query, right? Let's say our query is as here. Where is it? LangChain memory, where we wanted something about infrastructure and aviation. Okay, let's create this query like this. Okay, this is our query, and we just simply call Q&A chain.invoke, and we pass a query, and then we just print the response. You will see here, where is it again? Okay, so we are asking just infrastructure and aviation. Normally we have some text about infrastructure, but not about aviation. Okay, and if we try this out, we do Python rag. Oh, we first go into Python frameworks. Oh, CD framework, sorry. We activate the source EDI /in/activate. Okay, that's done. Now we can do Python rag and then LangChain rag. So if you ask for this, you will see that the process is a bit longer here. It's getting some information from our vector store. It's actually first getting the document, splitting the document, saving it in the vector store. We need to do it this one time, right? This whole thing one time when you have the document. So you don't need to do it every time you run your code. And then this step is actually just getting the information from the vector store and then using it to add the context to the LLM, which is what the retriever is easily doing based on the query that you pass. And then you are able to get a response based on what you ask for. So you can see here that we don't have something specific about aviation, which makes complete sense, right? Now let's ask something that's actually part of our document, which is maybe this, okay? This query here. we have the document is actually RFS from YC talking about startup and LLMs. So we have something about infrastructure and LLMs. Let's access, taking some time. And you can see the difference now. When you get real information, the AI is actually able to process and say, oh, I got something from the context. And this is what this is the answer you're looking for. Okay. Startup fund project related to infrastructure for LLMs in the context of compliance and all these tasks. So this is based on the data that has been extracted from our document. So you can see how easy it is to create a RAG with LangChain. Normally creating a production ready RAG is a bit more complex than this. And as I mentioned in the last video, I will do a complete separate playlist about that. And I will also put a playlist in the description so you can go through the LangChain official tutorial on how to create a complete RAG. You can have much more advanced topics there. With that said, let's go to the next part, which is doing the same thing with Haystack. Okay, so with Haystack, we somehow have the same process, but we have a more verbose code, because we need to create a pipeline to do everything. We need two pipelines actually. As you can see on the image, we have the first pipeline to index the data and put it into a vector store. The second is just to query the data, and for that we need a lot of libraries. Okay, so the libraries here are just OS and path as usual. I don't think we need OS actually. Okay, we need pipeline to create pipelines. We need answer builder to build answers. We already saw this in the past video. Prompt builder to build a prompt based on some templates. The OpenAI generator, the PyPDF document, the OpenAI document embedder, quite important, to embed this document and save them in the vector store. The document writer to write this document in the vector store. The in-memory embedding retriever to retrieve data from the in-memory vector store. The in-memory document store, the OpenAI chat generator, just to use the LLM. The OpenAI text embedder, this is to embed the query that you get from the user. So it's not a document, it's actually just some text. And you get this text, you pass it to your same model, and the retriever will go to the vector store and get the related documents. I think we imported this twice. The in-memory store already, the Py same document cleaner. Okay, this document cleaner is just some other process part of your pipeline to just make sure your document is clean, remove some extra things that may not be necessary. Same for splitting here. We already talked about that. It's just chunking the documents. Document writer, already imported. Chat from builder, and then chat message. I will show you how to use this later. So now, first thing first, we need to load the env to have the variables as well. Okay. Okay. Then we need, as you can see here in our LangChain Haystack. Is it the right one? Yeah, I think Haystack text. We had somewhere here prompt, but this prompt is really basic. We do not have some kind of for loop in there and many other things. And also this is made for compilations. So if you want to use a chat model, we need a chat template here that will say chat message and pass the prompts. Okay. So what we need to do here is to create a new template, a new prompt template that's a bit more advanced than what we did before. And I will explain that to you here. Okay. So here you will see that we have a for loop. Okay, it's like a templating engine. We look over all the documents and we print the documented content. We did that somewhere here, if you remember. Where's it again? Haystack. We had oh no, it wasn't there. Okay, so in the first tutorial about Haystack, we did that, looping through the documents and printing the document that we have. So here it's the same thing, but this is in our prompt. So Haystack will take care of getting this document object and looping and feeding the context with this list of documents. And same for the question that we'll need to fill up. So the query that the user will be sending us. With that, now we need to create our document store. And as usual, we're using an in-memory document store. You can replace it with any other document store available on their website, and it will work properly. Now we need first to index these documents. This is the first pipeline. As I mentioned in the breakdown of Haystack, everything in Haystack is actually a pipeline. So you need an indexing pipeline. And this indexing pipeline, we just create it by doing something like this, indexing pipeline. And then we add all the components to this pipeline. So we have the first component, which is converter. This converter will just take the document and convert it into text. The cleaner will clean the document. The splitter will split the document in sentences. The embedder will embed the documents, and the writer will write the document in the vector store. Pretty simple. This is clear and straightforward. Complete process to pre-process your data and save it in the vector store. Now we need to connect them. Okay, we need to say when you go from converter to cleaner, cleaner to splitter, and order. So we do it like this. So normally you can just say from converter to writer. If you want to, I'm just trying to say that you can go from the first component to the last one. You don't have to say first, second, third. It's free. It's up to you. So here we connect the converter to the cleaner to splitter, splitter to embedder, embedder to writer. So what we need now is just an index pipeline that run, and we pass the list of documents. But before that, let's create our second pipeline. Our second pipeline will be about retrieving the information and passing it to an AI, right? To the LLM to get the answer from it. So this is our sample pipeline. The sample pipeline is our RAG pipeline that will get the first embedding of the query, of the user query, okay? This first component will transform the user query into embedding. So let me show you that in the browser. So as you see it here, we have a question, and we need to transform this question into embedding and get the related documents to it. So that's what our first component is doing, getting this text, transforming into embedding, and the next will be retrieving the related documents to that text, okay? Okay, so the second will be to retrieve the related documents, as I mentioned, using our document store that we already have up there. So it will be saving in the same document store that we'll be using to retrieve the data. And then we need to add more components just to contact the LLM and get the answer. So when we get the documents here, we now create our prompt. I will show you that in the connection, that we go from the retriever to the prompt. And then this prompt is passed to the AI model here. And this AI model is actually used to generate the answer. So now the connections between our modules is here. That we say, okay, we get the text embedder, it will give us back embeddings, and the retriever query embedding is the part that will use the result from this. We'll use this embedding as result to go in the in-memory retriever and get the right documents. And the retriever will be, the answer from the retriever will be fed to the prompt builder, and the prompt extracted from the prompt builder will be passed as an LLM messages. Okay, will be passed as a parameter to this LLM messages. Same. We can simply grow our architecture so you can see. So if we run this, you just need here Python RAG and then Haystack RAG. It will create an image here if everything is right, and this image is this one. You'll see that this is a bit more complex. You have the text embedder, creating the embedding and passing it to the retriever, and the retriever will get some documents and passing it to the prompt builder, and the prompt builder will actually just get some prompt and pass it to here, our LLMs, as messages. I think maybe yes, and then this LLM will get the replies, and it's the end of our pipeline. Okay, so we can comment this. We don't need it anymore. So what we need now is to create the documents, pass the document to the indexing pipeline, and then get the query and pass the query to the RAG pipeline and try to get an answer. So first, we just create our PDF loader here. We convert this, we apply it to our file, our startup file, to get a list of documents. And then we call our indexing pipeline to index these documents, So the result from this will be splitted text, as you can see here, embedded and then write splitted text written into our vector database. Okay. So at the end of this, we have a vector store with all the embeddings and the related data. Now, the second step is to just get a question like this, okay, the query, and then ask to the RAG pipeline to generate an answer based on that. So this part here needs to be run one time. And this part is what you are doing when the user asks for a query every single time. But in our case, we're using an in-memory store. So if you run it separately, you can actually store it on the file system. But if you run it separately, you may lose the data. Okay. So here we have the query, and we run our RAG pipeline now and saying, okay, use this text for the text embedder, pass this question as the text. Okay, it will get this question, apply this first OpenAI text embedder to it, and then pass it to other layer of our pipeline. And then for the prompt builder, we need also to pass the question. Okay, because in our prompt template here, we have a question parameter. Great. And then we just call this and get the reply. So let's save this. And then try to call this again. Taking some time. Okay, so you can see the document highlights several key about infrastructure and LLMs, increase the amount of compute resource, need for innovative infrastructure solutions. So this is actually generated by AI based on the documents that we pass in our pipeline. And you can see that maybe this is a bit longer, but it is clearer and simpler to build, in my opinion. You have a more structured way of working, and you have a better understanding of what's happening in your application. Here, you have a lot of abstractions, which makes it a bit complex to know what is actually going on in between your processes. But with the pipeline structure here, you know exactly what's doing what and who is passing which information to which other layer. So you have a bit more control over every single part of your RAG pipeline. Okay. So with that said, let's go to the last one, which is LLamaIndex. We need to pass a RAG here to make sure we avoid cyclic import. And you will see that with LLamaIndex, it's kind of the same as with LangChain. It's easily, pretty abstracted. So we have and simplified as well. We have here, as usual, PDF loader, the path to just path the specific path, syntax splitter, vector store, the OpenAI embeddings, and then .env, and then we load .env as usual as the first step to get the environment variables. Now we put two settings. The settings will be the embeddings model and the chat model, the LLM. So the global app will use this in the process. Okay. So, and here we load our documents. Okay. We load our documents. Same. We actually talked about it here. Where is it again? LangChain. We did it here already in the last video. We load the document, and here we actually just faded the whole document to the app. But the difference here is now that we are saving the document in some vector store, retrieving the related chunk of this document to feed it to the new LLM. Okay. So now you will see how easy it is to parse this document, chunk them, and save them in a vector store. You create this node parser, and you pass your chunk size here. It can be 1,000, it can be whatever you want. And then this node is kind of simple. You just get the nodes from the document, and then you create a vector store, and you pass this node to this vector store. Okay. Now this vector store here will save things in memory, but you can create a new instance of this vector store with the separate vector store that can save things in a real database. Okay. And when you have this index, the simple thing that you need to do is to transform this index to actually be an engine query engine. So we can directly do what we did here, which is getting the embedding, retrieving, all the process from this indexing here is actually simplified here as index as query engine. Okay. And we get the top 5 documents. With that said, the only thing remaining here is just to get an answer from our LLM. So we get the same thing, query, engine the query, and we get response. So you will see that the step between saving the data in the vector store and querying it is pretty simple here and extremely abstracted. Okay, so we can try it. We can try it now. RAG, and then llama index with the RAG. Okay. The report discussed the need for new startup and at-risk key areas like data center, compliance, and other. So if you ask the same question as we had here in Haystack about what insight about LLM infrastructures, And also the size of the response, the quality of the response actually depend also on the quality of your prompt. So feel free to change this and modify this. But in general, this is how you do the simplest RAG possible with these 3 different frameworks. So you can see how many abstraction a framework has over on other framework, how easy it is to use one framework over another framework. So you'll see here the document is connected to fast and most effective data center. It's actually what the document is talking about. So they are pretty right here. And you saw it on the top here that when you have nothing about, so when the model do not have an answer about what you're asking for, the model can say, oh, I don't have any specific information about this, which prevent a lot of hallucinations, right? Yes, so concerning the project, as I mentioned in the beginning of the video, we'll do it separately on the channel. So it's just the need for me to have enough time to build a really complete project and get into complex topics instead of simple projects, so you can actually learn something really meaningful. Okay, so in the next module, we'll talk about AI agents. I hope this RAG module were completed enough for you to understand and have a better overview of recursive augmented generation. Thank you for watching, and see you in the next module about AI agents.